Okay, now I will like to discuss a little bit details how this operation is also known as a two-dimensional convolution. Okay, because there's something missing there, and I don't want you to confuse between this convolutional operation and the one-dimensional convolution operation, because something missing there. Okay, now let's discuss what are the different, and we try to minimize the different now, because we want you to relate with the previous course, so it's more meaningful for you to learn actually how this one relate with that one. Okay, now let's get back to this whiteboard. Okay, so again, this is a two-dimensional convolution process. I have already explained to you how to interpret this expression, okay, by having a sum of product, and you have a kernel, you have the input image. You just do a sliding process from the top left to the right bottom. Okay, you are sliding in that direction, and then everything overlap, you must multiply, and then you sum up together to obtain each and every pixel inside the image, to obtain the output image, which is the gxy. Okay, if you remember, some of the convolution properties that doesn't matter you are convolved between xn and hn, or you are starting convolve hn with xn, you will end up with obtain the same value yn. Okay, doesn't matter which position is it, yn with hn or hn with xn. I'm sorry, xn with hn or hn with xn, you end up with obtaining the similar yn there. Okay, so if you remember, when you do the convolution in one-dimensional signal, I just obtain the same, I just draw the same example as in this slide there. Okay, you have for this example, it's a good example there actually, this one. Actually you have given the input xn is this one, and then hn is one, and then because when you draw the diagram there, it seems to be, since your xn is very is represented by only two impulse response, okay, that point. So instead of xn convolve with hn, it's better for obtain the hn convolve with xn, because when you talk about the convolution process, if you remember, you need to flip one of it. Okay, either you flip xn or you flip the hn, because your xn in this example is very simple, so that's why you choose this one to be flipped. So that's why you put the xn after the hn in order for you to do some convolution. Okay, then after that, after you choose this one to be flipped, okay, this is where the operation, you just flip your xn, then you do a sliding windows there, your xn to your hn, you are do sliding into x direction. Okay, remember, so that is why if you relate this operation now with your two-dimensional signals, okay, okay, before that, once you do you are sliding there, you overlap between your hn and xn. Okay, once you do the overlappings there, then you get your x0, I'm sorry, y0, y1, y2, and so on. Okay, so everything overlaps there, then you are multiply together. So that's where the sum of product have been, that we be talking about the sum of product before in two-dimensional signal. So same goes to one-dimensional, that one-dimensional signals. Actually, when you're multiplying anything overlap, and then the one that not overlap, of course you are multiplying with 0 there, then you get 0, and you sum up together for every element that you produce by multiplying. So that is actually known as sum of product. So similar to two-dimensional convolution. Okay, just the difference is just in this course they don't mention about the sum of product. Okay, actually the operation is known as a sum of product. You multiply first, then you sum up together. Okay, when you do a sliding windows there, okay, you are sliding your xn into your hn in this case. Okay, because you are flip your xn, then you're sliding your into the hn there. Okay, now so you do it one by one until you get the last output is this one. You're sliding into this point, this point, and this point, and so on. Okay. Okay, now okay, so now let's relate this operation, the sliding process, and as sum of product there. I already mentioned sum of product, you're already clear about that. And then I already mentioned how actually the sliding operation there. So now let's go back to our two-dimensional convolution. If I try to draw our signals there, try to relate with our try to relate with the one-dimensional signal there. I try to draw our image in impulse response form there. Assume this is your input image. Of course, this is your hn, or in image we call it as w's there. And then what we do, in order for us to do a convolution, we must flip one of it. And most of the time, if you talk about the image, we always flip this one. Okay, we always flip this one. We don't choose either to flip xn or hn, because in most of the time in image, okay, this one is always very small. Okay, it can be 3 times 3, okay, 3 times 3. Okay, I draw it in matrix. It can be 3 times 3, it can be 5 times 5, can be 3 times 3 like this one, can be 5 times 5, can be 7 times 7. However, for input image is a big matrix. Okay, it can be 1024 times 1024. So it's very tedious to choose this one to be flipped. So that's why most of the time for two-dimensional convolution, we always choose this point to be flipped. Okay, the question is, let's say your wxy matrix is like the one in the slide there, which is this one is a 3 times 3. Okay, let's say that is your 3 times 3. If I draw this point over here in matrix, then actually is a 3 times 3. Okay, 3 times 3. This is your wxy. So the question is, the issue is, when I explained previously, when I doing the convolution, two-dimensional convolution in this slide, I don't explain about the flipping mechanism. Okay, but if you remember, if you talk about the convolution process, the flipping mechanism is important, or is essential, because if you don't flip the one of either xn or hn, then that is not convolution. You are not okay. You must flip one of it, then after that you can slice into the entire image. But in two-dimensional convolution, it seems to be we flip, or we skip the flipping process. We just directly take the window, or take the filter. We just do a sliding process into the entire image. But because this is a two-dimensional signal, so that's why instead of you just sliding in y-axis direction, we also slice into in one-dimensional signal we are sliding into x direction. But in two-dimensional signals, for convolutional process, instead of just one direction of sliding process, we are applying a two direction, meaning that's why we start from here, and then we slide into that direction, which is our, okay, if you talk about this one, actually this is our x direction. And then we also slide into Okay, we slide into y direction as well, so that's why you are sliding in that direction. There's a two direction of sliding process. Okay, now the sliding there is seem to be very clear. We need to do a sliding process because sliding process is one of the process involved in convolution. But the issue is, in this discussion, why we skip the flipping process? Because in one dimensional convolution we need to flip. Okay, we need to flip either xn or hn. Now in this case we don't flip the kernel. Why we don't flip the kernel? We just directly take the kernel and slide into the entire image. Okay, we need, if we want to delete this operation with the one dimensional operation, then we should not skip the flipping process. Otherwise it's wrong. It's not called as convolution. But why I skip that? Is it something missing there? Why I miss, or why I skip the flipping operation? Okay, the reason is that it's because, okay, this one you need to remember. Okay, why we skip the flipping process in two-dimensional convolution? Okay, actually the flipping process is happen. Okay, if you want to flip our w there, okay, actually you need, if you flip the hn, you just flip in that way. Okay, in that way means that any negative will become positive, any positive will become negative. So that is what you do here. Okay, flipping process. Okay, but in this case you are flipping your hn. In two-dimensional convolution you are also do the same. You are flipping in two direction. First you are flipping your x here. Okay, you are flipping in this direction, you just flip that direction. Once you finish flip in x direction, you need also to flip into y direction. Okay, that direction. So let's say this is my window or my kernel, then I need to flip this way. Once I finish flip this way, then that intermediate output I need to flip in that way, because I need to flip in two direction, because this is two-dimensional convolution. Okay, so that's how the two-dimensional convolution works. Now the issue is, why it seemed to be in my slide there, in this slide I don't do that at all. Why I don't discuss about flipping the flipping operation? This is because in image processing, most of the time the filter coefficient W over here is always in form of symmetrical. Okay, for example, later you will see one of the filter is also known as averaging filter. Okay, averaging filter, the W of the filter, okay, the filter is the W of the filter, okay, the W of averaging filter is look like this. Each element inside the filter, or the filter coefficient inside this matrix, is always 1. Everything is 1. Okay, meaning that even you are doing the flipping process in this direction and this direction, you still get the same 1 1 1 1 1 1 1 1 and 1. Okay, so that's why we skip all of this. Again, we skip the discussing the operation, or we just ignore the flipping operation in two-dimensional convolution if you talk about image processing, because the filter coefficient is always in a symmetrical structure. So that's why if you flip in that direction, you still get the same output there, same as the input there. So same as the value of the output there is similar to the input filter coefficient. So meaning that even if you skip the process, you still actually get the same values. Okay, so hope this thing is clear. And actually now please don't confuse between one-dimensional convolution and two-dimensional convolution. So even we don't discuss in this operation about the flipping process, because the reason is because this window is always in symmetrical structure. So if you flip as well, you still get the same structure or the same values. So that's why we skip of doing a flipping operation. We just directly take the value and do a sliding process to the entire image. So I hope you clear about the convolutional operation or two-dimensional convolutional operation, which is related to a kernel based processing. Because okay, again I would like to summarize everything is there. Why we call this operation as a kernel based neighborhood processing is because it's dealing with the kernel or window, and everything that dealing with the kernel or window is also known as a convolutional, a two-dimensional convolutional operation, because you are now doing the convolution between the input image and the kernel or the window. Okay, so that's why they call it as a kernel based neighborhood processing. And the word neighborhood processing again, why they call it a neighborhood processing is because now if you see over here, the transformation function to obtain this S7, okay, to produce S7 you must fit not just R7 into this transformation function, you also need to fit R2, R1, R2 and so on, which is the neighbor of this R7. So that's why they call it a neighborhood processing.